Welcome to the latest episode of the MFG Radio Network's Lunch and Learn, as we highlight some of the latest advances in manufacturing and design, gain insights about the newest products and technologies to move your manufacturing ahead of the competition. Hello and welcome to our next Manufacturing Lunch and Learn here at GIE Media. I'm Jake Kaufman, a managing editor for the manufacturing group at GIE. Today we'll be joined by Mugi Franken as they discuss strategies for reducing machine time and tools in challenging 5-axis aerospace parts. Mugi Franken, headquartered in West Boylston, Massachusetts, is a wholly owned subsidiary of German parent company Mugi Work Richard Glippel KG, a learning manufacturer of precision taps, thread mills, drills, end mills, tool holders, clamping devices, and other rotary tools for over 100 years. Over 10,000 types of high-performance cutting tools and accessories are stocked in the United States, with over 40,000 items sold through distributors worldwide. Since 1984, Mugi Franken USA has established itself in North America and significantly broadened its capabilities, expanding its facility to over 50,000 square feet. Today, the West Boylston facility includes a technology center with a machine and tooling demonstration showroom and classroom, tool manufacturing and coating, reconditioning, warehouse, sales support, and administrative offices. Mugi Franken's Technology Center is a research and development facility for North American manufacturers designed to be a resource for applying cutting tool application strategies. Application engineers are available to provide programming assistance and process recommendations, as well as to perform test cuts so that manufacturers do not have to tie up their own production resources. Now, today's presenter is Evan Duncanson, a milling application specialist at Mugi Franken. Evan has more than 14 years of technical and engineering experience in metalworking manufacturing, most recently as Mugi Franken USA's milling application specialist, providing focused application support for complex milling applications. Evan has been with Mugi since 2016, beginning in technical support, where he was the primary machine programmer for testing customer parts and conducting machine demonstrations. Prior to that, he worked in engineering at a high-speed, high-precision machine builder and supplier. Evan holds a degree in engineering. Now, today, Evan will present strategies for reducing machining time and tools in a challenging 5-axis aerospace parts. Attendees can gain an understanding of the milling tool options available, as well as strategies for applying them to reduce tool consumption and optimize 5-axis cycle times. So without further ado, Evan, the floor is yours.
All right, so we're going to be going over 3 different topics today, 3 different tooling options today. The first one being Ceracut. So Ceracut is our version of the ceramic end mill. Obviously, ceramic end mills have, been around for a little while, and this is our version of it, and we'll go over some key features of it. So obviously, with ceramic cutting, they're used for, heat-resistant super alloys like Inconel, nickel alloys, that kind of stuff. They mill much, much, much faster than standard carbide end mills because they actually, liquefy the material and get it out of there with heat rather than trying to really make a chip, if that makes sense. They they have up to 5 times better life than standard carbide end mills in the same kind of strategy. And what's very interesting about our ceramic tool is that it's actually a solid carbide shank brazed to a ceramic end. And we'll go over why that's a very good construction in a minute. As far as cutting speed is concerned, so obviously with ceramic, you're going much, much, much faster SFMs, and cutting speed, than a traditional carbide tool. So you can see here on the left, that was at 800 SFM, and on the right, it was 3250 SFM. What we're seeing here is, 800 SFM in Inconels or in nickel alloys is still extremely fast, but it's not fast enough for the ceramic tool, right, for the Ceracut. So we want to get really, really high RPM, high SFMs with these tools. so we can really just remove that material as fast as possible and get it really high heat, right? And you can see all the cold welding and everything like that on the lower SFM version. So the chips that come off of a ceramic end mill, they're kind of like dust, right? You're not going to see a standard chip formation like you would with a carbide end mill. You're going to see more dust and kind of burnt, chips, burnt material. That's perfectly fine. That's normal with these tools, and we don't suggest using coolant because of the high heat. So obviously, if you're trying to liquefy the material, get that material out with heat, we don't want to cool the material with coolant, with a liquid-based coolant, and it can actually cause thermal cracking in the ceramic itself, and essentially make it explode. So we just want to use air if possible. You can use cold air or just regular shop air is fine as well. But that will help cool the workpiece and the tool, but not interrupt the heat of the cutting action. So here we can see the duplex geometry of the high feed Ceracut. So it's a high feed geometry, so it's got that dual radius on the bottom there, and what that allows us to do, it gets very high chip loads, and we can go significantly faster than we could with a square corner or just like a corner radius tool. So it's got 5 equal flutes, negative front rake face angle. So actually the rake face, what's actually cutting the material is actually negative. So it's really not cutting the material, it's just pushing the material out of the way. And that's perfectly fine in this kind of application because it produces more heat. So it actually liquefies the material better than it would if it had a positive rake. And then the type H geometry just means that it's the geometry used for our hard milling tools. So this tool can actually be used in the nickel alloys and, those hardened materials, 60 Rockwell plus type of thing. You can also see the dual construction here at the bottom, the ceramic end that's brazed onto the carbide shank. And what that does is you don't think of carbide being vibration dampening, right? It's a very rigid material, but compared to ceramic, it's very vibration dampening. A piece of ceramic has no dampening abilities at all, right? So when we combine the two, we then are able to get vibration dampening out of the carbide, but still have that rigidity and the performance of the ceramic end mill. And then you can see here, so this was our Ceracut after, at end of life, after cutting some 718. And then on the right is a typical tool from a competitor. That's usually what you would see when you're done milling a ceramic tool. But with our tool, you should be able to see a good wear, not a lot of material buildup and everything like that. And the Ceracuts can actually be reconditioned because of that. So that's the first time that we can, offer ceramic reconditioning on that. All right, so next we're going to get into circle segment. Circle segment's a fairly simple concept, but sometimes it's hard to wrap your head around it. So essentially what it is taking a segment of a circle, very large circle, 3 meters in diameter in some cases, and zooming in on it and taking that little section of it and putting on a smaller tool, a 16 millimeter diameter shank tool or something like that, right? And we'll get into exactly what that means and how to utilize it in a second. A cost comparison over 50 parts of using a taper form. You can see here that the light gray is your total cost, the dark gray is your tool cost, and then the cycle time is your orange there, right? So your tool cost, obviously a circle segment tool is going to cost a lot more than a regular ball mill. There's a lot more technology in there and it's a lot more specialized tool, but your cycle time is going to be significantly reduced, right? So you'll see, a significant decrease in your cost overall because you're going to be moving parts in and out of your machine way faster, right? And it's a 70 to 90% cycle time reduction usually. So the different types of circle segment tools we offer taper, oval, lens, and barrel. And we'll get into what exactly those mean. So the taper form is, in my opinion, the one I start with all the time, right? It's the one that you're going to get the most amount of benefit out of, right? And that's because it has the largest cutting radius versus shank diameter, right? So we have shank diameters from 6 to 16 millimeters, and the cutting radius from 50 to 1500 millimeters. So that means you could use a 16 millimeter shank tool, but you're essentially using a 3 meter diameter ball end mill to finish your part. But because these have such large radiuses, they're locked at certain tip angles. And you can see here that we have the taper form A and the taper form B. So the taper form A is between 12.5 to 42.5 degrees. And then the taper form B is between 60 and 70, right? So, one tool will be locked at 20 degrees. You have a little bit of play back and forth, maybe a degree or so, but it's locked at that 20-degree angle. And that's because it has that large radius, right? And a lot of people use these for these, aerospace structural components like that, finishing those walls, right? They have very, very small corner radiuses in the corners there. The next shape is the oval form. So the oval form, I believe, I would say is the most versatile shape. And that's because it has a slightly less radius to shank ratio, right? So the shank is from 6 to 16 millimeters, and then the cutting radius is from 50 to 95, right? So because it has a smaller radius on it, still very large, but a smaller compared to the taper form, you're able to get into some spaces that normally you wouldn't be able to get into with the taper form, right? And it can be tipped at many different angles. So it's a little bit more versatile, a little bit easier to use sometimes. But you won't get as much cycle time savings as the taper form. And then you have the lens cutter. So the lens cutter is really only end cutting. It's from 4 to 10 millimeter shank diameter and from 6 to 25 millimeter cutting radius. So it's a little bit smaller than the oval form, but it's only end cutting, so it's usually used for, shallow floor finishing, like a tire mold like this here. And then the last shape, we don't get into this shape that often. It's the barrel form. We only offer one size. It's a 10 millimeter shank with a 50 millimeter cutting radius, and it's really only used for undercuts. So you can see here, this part here has a little bit of a concave undercut there. So that's why I would use it on that. We also have a couple of expansions in our circle segment line. So we have the taper form and the oval form recently came out with doubled the flute count, essentially. So where you had 2, you had 4 now, and where you had 3, you have 6 flutes now. So obviously that allows us to cut higher hardness materials up to 60 Rockwell, but it also allows us to go faster, right? More flutes with the same chip load, you can go faster. So if you're using this in, a titanium or stainless or something like that, and the high flute count isn't going to get in the way, you can actually, go that much faster. Then we have, the roughing profile oval form. And you would say, why do I need a roughing profile on a circle segment tool? I thought it was a finishing tool, right? This is a semi-finishing tool. And the reason for this tool is really blades, right? If you think of a blade, it's long and it's thin, right? If you try to take a blade, from the roughing stage here on the left, you have a lot of material still on that blade, right? If you try to take that and put the circle segment tool directly onto that blade like that, it's going to be cutting a slight amount of material here and a large amount of material here. It's not going to be able to do it very well. And you're going to get witness lines in the surface from the different amounts of material, right? So this roughing oval form does what you can see on the right here. So it takes off all of that material after roughing and creates a consistent amount of material all the way across the blade for then the finisher circle segment tool to come in and finish, right? Then you're going to much, much better surface finish, and you're going to protect your circle segment finisher from all the abuse, right? And this tool, it's got a flat bottom on it, right? So it's not to a ball. So it's very, very sturdy. It can take off a lot of material at one time, and is very, very stable. And what's nice about the circle segment tools is they cover pretty much the entire range of materials, right? So here you have our material breakdown. You can see everywhere that has a filled in black dot, that means that's the best tool geometry for that material. Everywhere that has an open dot, that means it'll work, but there's probably a better tool for that material. But you can see pretty much all materials have a black dot, and if they don't, they at least have the open dot. Now, circle segment tools are very cam intensive, right? So you need to have a cam software that can really, really utilize that geometry and that technology, right? So Hypermill, we developed the circle segment technology with Hypermill over in Germany. So they're always the front runner, right? They are always the one that has the best support, right? Mastercam is very, very good. They're right behind them. And then you got some of the smaller guys. You got, Concepts, NREC that have a fantastic software for doing blades and bliss and stuff like that. Esprit, CATIA, Annex, so on and so forth, right? You just need a good CAM software that can actually utilize those tools and bring them in and, have the step files in and everything like that. Little application example. So here we have the tool paths out of Hypermill from a 1/2-inch ball mill and a 16 millimeter taper form. So you can see how just dense and populated the tool paths are of the ball mill, and how spread out and sparse the tool paths for the taper form are. And we had a 6.3 thou step down with the 1/2-inch ball mill, and then a 79 thou step down with the circle segment tool with the taper form. And both tools create a same scallop height or calculated scallop height of a 1/2 micron high. But then you have the speed, right? So that tool path with the 1/2-inch ball mill is going to take almost 2 hours. And then with the taper form, it's going to take 21 minutes. It's an 81% cycle time reduction, right? This next slide is my favorite slide of the presentation. So this is a actual representation of this part, which is about 6 inches tall, next to what the taper form tool would look like if it was a ball mill, right? So you can see at the bottom there, that's the part, right? Like I said, it's about 6 inches tall. And then what you're looking at on the top there, that's a 3-meter diameter ball mill, right? Obviously, you would never be able to touch that part. You'd never be able to find a holder or a machine that could hold a 3-meter diameter tool, a ball mill. But essentially, that's what you used to finish that blade, right? But it was just a very, very small inch long or so segment of that 3-meter diameter ball mill. Pretty crazy. The next tool we're going to go over is the cut and form end mill. So the cut and form end mill is a very fine, high polishing tool for non-ferrous materials. And the reason why it's called a cut and form is it actually has 3 cutting teeth and 3 burnishing teeth. You can see over here on the right, we have the red is the cutting teeth, and then right behind it is the burnishing teeth in the green, right? So they don't cut anything, they just push, right? So you cut a little bit of material, and then right after that, you push the material back in on itself and polish it or burnish it, right? And what's interesting is, say on like a 10 millimeter tool, the burnishing end mills are exactly 10 millimeters, but the cutting flutes are 9.99 or 10 microns smaller than that, right? So you're always going to hit the burnishing flutes on the rotation there, right? So the cutting flutes will come over, and then it has 10 microns of, burnishing. And then a little application example. So this was in some 6082 material over in Germany. They ran that at a little over 1,000 SFM, 1 thou per tooth, 30 inches a minute with a 4 thou radial depth, right? So they were just doing a 4 thou finish cut. We suggest using grinding oil or cutting oil for the best results. That's how you're going to get the best surface finish because you need that lubricity. Emulsion can be used, but the filtration is a huge factor, right? If you have any kind of particulates in your emulsion coolant, those are going to get pushed into your surface, obviously. Right? And they were able to achieve a 0.08 RA finish, right? Just by using this milling tool. So if we look at the surface finish roughness table here, straight out of the machinist handbook, and you see that's where we're at, right? That red line is where we achieved for surface finish. And here you have the milling category, right? So milling nowhere near where we are, right? Traditional is, 0.8, not 0.08. And then if you keep on going down, you're at barrel finishing, grinding, honing, lapping, right? All that kind of stuff. But you're using an end mill to be able to get those finishes, right? So you don't need to go to another setup. You don't need to go to another machine. You're right on the same machine. Yeah, you might have to use some oil or something like that or have better filtration, but you're still using the same exact machine, the same exact setup to get these amazing surface finishes on non-ferrous materials, aluminums, coppers, brass, that kind of stuff. All right, so that's all I had today. So we'll open it up for some questions.
All right, Evan. Well, thank you so much for that presentation. So looks like we do have a few questions. So the first one I have for you, Evan, is how can I test new end mill technology without tying up current production?
Yeah, that's a great question, right? I mean, tying up a machine that's currently running in production, that's going to be a difficult thing, right? You're going to have to pull. Yeah, so difficult question there, right? The great thing that we can offer is we can actually offer some support in that at Imugi in West Boylston, Massachusetts, right? So we have several people who can program, different softwares, Hypermill, Mastercam, all that kind of stuff. And then we have several machines in house at Imugi, mainly our Grobe G550A machine that we can run tests on. I'm actually going to do one this afternoon on a Ceracut on some crazy Inconel material. So we can actually test the tool, test the strategy, and everything like that, and potentially make a part for you or something like that, video it and everything, and you guys don't ever have to touch your machine.
We also have a few other ones. So next up is there a calculation available that can help determine the cost savings when using new end mills compared to what they're already using?
Yeah, so specifically with the circle segment tool, we do have a calculator online. I believe you can find that on our main website, and you type in all of the stuff that you're currently using, what tool, how much it costs, your step overs and everything like that, and then it'll spit out a calculation. It's fairly rough because it doesn't know your geometry of your part and everything, but it'll spit out a calculation of how much savings, time, cost, and everything like that you can get out of that. And then to take that a step further, we can do that for you as well, right? So we can look at the part, program it, and everything, and then give you an idea of how much you would save.
Awesome. Thank you, Evan. Also, it looks like Chris in the audience wants to know he cuts and forms end mill. He mainly cuts 70-75 and 60-61 aluminum. They only use emulsion. So, what kind of filtration should he use for the machines?
Yeah, so I suggest just an extra filtration system or a finer filter, right? Like a micron filter, 1 to 3 micron filter or something like that. Your machine builder can help you with that, spec that out, and just say, you're doing fine polishing work. You need as clean of emulsion as possible.
Okay, and then looks like we do have one final question. Talking about the circle segment, how do you know if circle segment is right for your application?
Yeah, so that would be another thing that you guys can come to us for. We can take your part and look at it in the CAM software and decide, if we think it's a good, safe bet or not. The general idea is if you're doing three axis or five axis finishing on a part with a ball mill, you might be able to put circle segment on it. It's not always 100% the case, but sometimes you can, or a lot of times you can take circle segment and put it on that. If there's a lot of like intersecting surfaces and a lot of crazy geometry, might not be a good candidate, but a lot of flowing, smooth surfaces that you have to use a ball mill for, that's a fantastic
Awesome.
scenario.
Thank you, Evan. We do actually have a few more coming in here too. So Steve would like to know for the burnishing tools, what is the recommended holder when using these?
Yeah, so I would suggest first of all our FPC holder. It's a mechanical worm-driven holder. Is very very good because it holds very very tight, but also has some dampening effects to it. I would not suggest like a heat shrink fit holder or something like that. That's just going to be too rigid. You actually want some dampening. You want to remove those vibrations from the machine. So like I said, the FPC or more of a like hydraulic holder that has a lot of dampening in it.
Okay. And also Matthew wants to know is how do you pick a tool type for vertical wall finishing with tilt? And also, do you have any tips on Mastercam programming using these cutters?
Yeah, so for a vertical wall with like a little bit of a tilt, I would go with a taper form for that. The taper forms are very, very good with, straight walls that are maybe at a tilt, have a small corner radiuses like I showed in the presentation, something like that. And then hot tips on Mastercam. There's one of my coworkers, Dan, is the Mastercam guy here. So he can talk your ear off for probably for hours on hot tips, Mastercam programming with those tools. I'm more the hypermill guy here. But get in contact with one of us if you get in contact with me and you want to use Mastercam, I'll send you over to Dan, but we can both talk to you about all of the tips and tricks that we've come up with over the years. And then also you can talk to the cam people as well. You can talk to the open mind who makes hypermill, and you can talk to Mastercam specifically on you know what they suggest, right? It's always good to have a couple of different sources, right?
Awesome. Thank you, Evan. And also, if anyone has any other questions concerning Imugi Franken products, they can always reach out and Evan can get back to you at a later time. So if the questions did not get answered today, you still do have time to get your answers. So I want to thank Imugi Franken once again, headquartered in West Boylston, Massachusetts. Imugi Franken is a wholly owned subsidiary of a German product parent company, Imugi Work Richard Glippel KG, which is a leading manufacturer of precision taps, also with thread mills, drills, end mills, and tool holders, clamping devices, and other rotary tools for over 100 years. They have over 10,000 types of high performance cutting tools and accessories stocked in the United States, with over 40,000 items sold through distributors worldwide. And once again, thank you very much to Evan Duncanson. I'm sure we'll be hearing from you back here at GIE Media soon. Thank you, Evan.
Absolutely. Thank you, guys.
You can find more Lunch and Learns plus the MFG Radio Network's other podcasts on Apple Music, Spotify, Google Podcast, or on our websites at todaysmedicaldevelopments.com, aerospace manufacturing and design.com, and evdesignandmanufacturing.com.